We now turn our attention to solving systems of inequalities, and when we're dealing with lines that are in slope-intercept form, I usually like to set up the following chart: greater than or equal to, less than or equal to. And I like to say that we shade above whenever we have a greater than, below whenever we have a less than, and then we have a dashed curve when the equal to is missing, and a solid curve when the equal to is present. However, this only works when the line is in y equals mx plus b form. The above-below rule changes otherwise. When you have a circle, then your greater than or equal to will refer to shading outside the circle, greater than the radius. And if you have less than or equal to, you will be shading inside the circle, less than or equal to. Now, if all fails, you also have the test point method, which always works to take a test point, determine whether the point works in the equation, and if it does, that's the region where you get the shading. So we start off with some cheesy problems here. Just identify, are these points in the solution set or not? So we're going to take these values and substitute them in. 2 times -3 plus 3 times 3, is that question mark over my greater than 6? In other words, is -6 plus 9 greater than 6? And the answer is no. Let's try that with a second point. Take the 5, -1 and substitute that in. 2 times 5 plus 3 times -1, is that greater than 6? That's 10 minus 3, which is 7, which is greater than 6. So the answer there is yes. And finally, with the 0, 2 times 0 plus 3 times 2, is that greater than, not equal to, greater than 6? Well, that just becomes 6 greater than 6. No, it's not, so no, that is not a solution. Now we want to graph the solution set here. Now you have some choices. Do you want to convert this into slope-intercept form? Personally, I don't. When it's in standard form, I like to graph by intercepts. If I let x be 0, I just have 5y equals 10, so y is 2. And if I let y be 0, I get 2x equals 10, so x is 5. So this line will go through 0, 2, and 5, 0. Because there's no equality here, this will be a dashed line. And the greater than, I know it's not in slope-intercept form, but once we subtract the 2x and divide by 5, it'll still be a greater than, which means shade above. So if I try a test point such as the origin here, 0, 0, and I substitute that in, 0 plus 0, is that bigger than 10? The answer is no, it doesn't work. And it shouldn't work because we've got our shading on the other side of the line. Now, how would this problem differ if there was an equal sign here? Well, basically the answer is it would be a solid line rather than dashed. And how would the problem differ if this was a less than instead of a greater than? The answer is we would be shading below a dashed line. So below the dashed line. Here we have another problem. I'm going to rearrange this here, put the y on the left. That would be 2y is less than 3x. And then if I divide through by 2, I have y is less than 3/2 x. Well, that line would be a diagonal line going through the origin with a slope of 3/2, meaning rise 3 and run 2. And because there's no equality included, this would be a dashed diagonal line. And in slope-intercept form, there's a less than here, which tells us we're probably shading below. If I want to try this with a test point such as 2, 0, I can substitute that in. 3 times 2, that's 6 is bigger than 2 times 0. 6 bigger than 0. It works. That means, yes, there is supposed to be shading below this dashed line.